Hello and welcome to Constituents of the Atom. So first thing I'm going to do is draw a simple model of an atom. We've got the nucleus in the centre of the atom and the electrons that orbit around the outside. Inside the nucleus we have positively charged protons and we have neutral neutrons. This is the nucleus of a helium atom with 2 protons in it, making it helium. If there are 2 protons in the centre, then we're going to have 2 electrons orbiting around the outside, balancing that charge. So we've got 2 negative charges and 2 positive charges. So overall, an atom is electrically neutral. Let's label some of the parts. So we've got the electrons, and they orbit around the outside. We've got the neutrons, which are neutral. We've got the positive protons. Yeah. Overall, this is the nucleus. So the protons and the neutrons form the nucleus. And sometimes you'll hear protons and neutrons referred to as nucleons. So a nucleon is either a proton or a neutron. Okay, so we say that the nucleus is filled with nucleons, for example. Okay, let's look at some of the properties of these things. So a proton and a neutron are almost exactly the same size. They have almost exactly the same mass as each other, but they have very different charges. The relative charge of a proton is +1. A neutron has no charge at all. The electron has the opposite charge to a proton, so it is -1. The masses, the proton and the neutron, are basically the same size as each other, and the electron is very, very tiny indeed. It is a very small fraction of the size of a proton or a neutron, and it is 1,840. That's the fraction. So it is extremely small, and yet if you look at the amount of charge that it has quite a large charge. In fact, we can calculate something called the specific charge, but before we do that, let's have a look at the exact numbers. These values here, these ones and -1s and zeros and very small fractions, are relative. So we are comparing the proton to a typical proton. We are comparing an electron to a typical proton. So compared to a typical proton, these are the relative masses and the relative charges, but these numbers are known more accurately, and we can express the charge in in coulombs, and we can express the mass in kilograms. So let's do that. So charge and mass. So actual mass, actual charge. So the charge of a proton is plus 1.6 times 10 to the minus 19 coulombs. The electron is the opposite of that, and it is minus 1.6 times 10 to the minus 19 coulombs. The neutron does not have any charge. The mass of a proton is 1.67 times 10 to the power of minus 27 kilograms. And the neutron is almost exactly the same. If I was to write these out to three decimal places, then the masses would be ever so slightly different. But we're not going to do that today. But to 2 decimal places, these nucleons have the same mass. The electron is much, much smaller. It is 9.11 times 10 to the minus 31 kilograms. If we calculate something called the specific charge, then what we're looking at is how concentrated is that charge in a mass. So specific charge is equal to the charge divided by the mass. And you can calculate that. And just looking at those numbers, you can see that with the electron being so small and having such a small mass, and yet its charge is exactly the same size of that of a proton, but with a much smaller mass, then the specific charge for an electron is much, much higher. And those numbers do appear on your data sheet. You'll notice as well that if you were to do this calculation for the neutron, you would be dividing 0, the charge, by the mass, and that will return an error on your calculator. So the neutron doesn't have a specific charge. Okay, let's have a look at isotopes. Okay, so the word isotope means a different version or a version of an element. The example that we've got here is hydrogen, and hydrogen has 3 isotopes. It has the isotope with a mass of 1, so just a single proton inside the nucleus. It has an isotope where there is a mass of 2, so we've got a proton and a neutron inside the nucleus. And we have a version where there are 3 nucleons inside the nucleus. We've got the proton and we've got 2 neutrons. So remember that the number of protons, so we've got 1 here, 1 here, and 1 here. The number of protons tell us that this is hydrogen. So you'll notice that these are all versions of hydrogen. There's no correct version, it's just that there are 3. It's almost like hydrogen is a triplet. The number of protons gives us the name of the element, but the number of neutrons, there can be 0 or 1 or 2 or more. These are the 3 isotopes of hydrogen, and these ones are quite fun because they actually have their own names. So hydrogen 1 has a specific name, protium. Hydrogen 2 has a name, and that's deuterium, and hydrogen 3 is known as tritium. So you'll notice that I'm referring to them as hydrogen and then the mass number, and that mass number is at the top. The number at the top is always the largest, that's the mass number, and then the number at the bottom is always the number of protons, the atomic number, and you'll notice that that's the same for all 3. Now, protium is by far the most commonly found hydrogen isotope in nature. Over 99% of it, over 99% of hydrogen is protium. A very small amount is deuterium, and if deuterium forms a chemical bond with water and you get H2O, but it's deuterium, then that water is going to be much heavier because the hydrogens are twice as heavy than regular water, and it's known as heavy water. Tritium is much rarer and tends to be manufactured. Let's have a look at boron. Boron is a good example. Boron has 2 main elements. We've got boron 10 and boron 11. Boron 11 is the most common in nature, with 80% of it, and only 20% of boron 10. So if you take a random sample of boron in the environment, 80% of it is going to be 11, and 20% is going to be boron 10. You'll notice on the periodic table that the mass for boron is written down as 10.8. And that's because some of it is 10, but most of it is 11. So the mass on a periodic table usually indicates the average overall mass when you include all of the different types of isotopes. And we can calculate that by taking something called a weighted average. So usually, when you calculate an average, you're assuming that every data point is equally valid when you're doing your calculation. But if you know that 80% of this number is important, but only 20% of that number is important, then we can do a weighted average to calculate that and take it into account. So for boron, what we would do is say, okay, well, 80% of 11 and 20% of 10. So let's add them together with those proportions. So we'd say 80%, 80 over 100. You may prefer to write that as 0.8. And we're going to look at 20%, which you may wish to write as 0.2. So we would combine these and say, all right, well, we want 80% of boron 11 plus 20% of boron 10. And that will come out as 10.8. And that is the mass number that you will find on a periodic table.